In this lesson, we're going to determine whether an ordered pair is a solution to a given linear inequality. In this example, we're asked to determine if the ordered pair 3, -2 is a solution to the linear inequality. So all you have to do to determine whether the ordered pair is a solution is by plugging it into the equation. If when you plug it into the equation and do the math, that you have a result of a true statement, then it is a solution. If, however, you are left with a false statement, then it is not a solution to the linear inequality. So let's go ahead and plug in this ordered pair. We're going to plug in a 3 in x's place, and we're going to plug in a -2 in y's place. When we do that, it's going to look like so. -2, but with a negative in front of it, becomes +2. 3 plus 2 does equal 5. Now let's read the statement now that we have one number on one side and one number on the other side. So reading this statement, it would read as 5 is greater than 5. Well, is 5 greater than 5? No, it's not greater than 5. 5 is equal to 5, but it's not greater than 5. So this is a false statement. And because this statement is false, that is your proof that the ordered pair of 3, -2 is not a solution of the linear inequality. In this example, we're asked to determine if 7, 1 is a solution to the linear inequality. Again, the only way you're going to determine whether an ordered pair is a solution is by plugging it into the equation, or in this case, into the inequality. If when you plug it in, you have a true statement, then that is proof that it is a solution. However, when you plug it in and you do the math and it's a result of a false statement, then that is your proof that it is not a solution to the linear inequality. So let's go ahead and plug this ordered pair in. We're going to plug in a 7 for x, and we're going to plug in a 1 for y. When we do that, it's going to look like so. Let's go ahead and finish solving the left side. 7 take away 1 equals 6. And once you get it where you have one number on one side and one on the other, then you can read the statement to determine whether it is a true or false statement. So let's go ahead and read it. It reads as 6 is greater than 5. Is 6 greater than 5? Yes, of course, 6 is greater than 5. That is a true statement, which means that the ordered pair of 7, 1 is a solution of the linear inequality. And there you have it. The second objective of this lesson is to graph linear inequalities in two variables using the test point method. Before we begin graphing, let's go over a few things about how you're to graph. Now, in terms of graphing, step 1, graph your line. You can use whatever method that's comfortable for you, whether that's graphing using the x and y intercepts or graphing using the rise over run method. Simply graph the line. Step 2, in terms of sketching your line, you're going to be either sketching a solid or a dashed line. If you have the less than or equal to or the greater than or equal to symbol, then you're going to sketch a solid line. If, on the other hand, you have just the less than or greater than symbol, then you're going to sketch a dashed line. In other words, have a space between your lines. Now, once you graph your line, your next step is to determine which boundary or region that you're going to shade or color. So the best way to understand which side you color, you can always use what is called a test point. And when you test that point, if you get a true statement, then you will shade that side. If when you plug in that test point, it results in a false statement, then you do not shade the side. In other words, always shade the true side, never ever shade the false side. So let's go ahead and do some practice problems so that it makes more sense. So in this example, we're asked to graph the linear inequality. Notice that the equation is in slope-intercept form. When it's in slope-intercept form, it is very easy to graph the line using the rise over the run method. And what that method is it would be step one to plot your y-intercept. Now the y-intercept, you know, here is in the back. It's 5 in terms of where the location is on the rectangular coordinate system. It would be 0, 5. Once you plot that point, then you're going to use your slope to rise and run to your next point. And because my slope is -2, that means I'm going to have a -2 rise, which when it's negative, you're going to actually fall down. So I'm going to fall down 2 and I'm going to run 1 because that is the way you would write the slope when you have a negative slope. So let's go ahead and first start by plotting the y-intercept, that is 0 and up 5. From that point, we're going to fall down 2 and run 1. That takes me to my next point on the line, and we're going to go ahead and draw what type of line? Notice here in the equation, it is just the greater than symbol. It doesn't have the line or equal to under it, so that means we're going to sketch a dashed line. Next, you want to determine what side of that line you're going to draw. Whether you're going to draw or shade to the left of that line or to the right of that line. Well, all you have to do using the test point method, we're going to use the test point 0, 0. And the reason we use that point is because zeros are so easy to plug in terms of math, you can easily get an output. Now our test point is located here at 0, 0, which means that if I plug that test point in and I get a true, that means every point on that same side with the test point will be true, and then that means you would shade that region. However, if I test the test point and I get a false, then that means I do not shade that region. By default, I will shade the opposite region, because then the opposite region would be your true region. So let's go ahead and determine which region we're going to shade. We're going to go ahead and plug in that test point, meaning a 0 for X, and plug in a 0 for Y, because we want to determine whether we should shade that test point region or not. So when we plug those points in, it's going to look like so. That's going to leave me with 5 on the right side. Once you get your statement, or you get it to where you have one number on one side and one on the other, you can read your statement. Let's go ahead and read it. It says that 0 is greater than 5. Well, we know that 0 is not greater than 5. That is a false statement. And since that region over where the test point is was false, that means every point on that side is false, which means by default, the true side would be to the right, and that would be the region we shade. And there you have it. graphing linear inequalities using the test point method.